Hello everyone, in this class we're going to continue with chapter 4, forces that are due to static fluid, but in today's class we'll look at, instead of a vertical wall, we'll look at an inclined wall, which is used in many cases, especially in dams. They use a inclined wall rather than a vertical wall, and the reason behind it is because first of all, the geometry, it has a wider base than a vertical wall, and second thing is the inclination. Okay, so we'll start with an example of an inclined wall that is holding back a static fluid, which we'll call as water. The fluid is exposed to atmospheric air, which we'll call the free surface. The depth, this is specific weight of water. The depth is h, we'll say it's 10 meters. Okay, the centroid, or HC, which is basically h divided by 2. Okay, and the angle of inclination, we'll say it will be 60 degrees, which is the same as this angle here. 60 degrees, and it's the same as the angle here. Okay, now this here is the side view of the wall. The front view looks something like this. Which is similar to the vertical wall, except that it's a tilted in an inclined angle. It's a rectangle that's tilted. That's the front view. Okay, that's looking at it from inside. Okay, now we'll assume that we're given the width of the wall, which in most cases you are, and the length is usually equal to h, the depth of the fluid. But since it's inclined, L is bigger than h. Therefore, we need to find L, and we can't assume that L equals to h anymore. Okay? We'll assume that the width is 20 meters of the wall, and we need to find L. So the area is basically width times height times length. That's the area of this rectangle that is exposed to the fluid. Now, in order to find L, we have to use a new approach. Let me just get rid of this here. The new approach is that this here, the length of this wall is called L, as I mentioned before, and the length from the surface to the centroid is LC. The length from the surface of the fluid to the centroid. And this here is HP, which is center of pressure. It's where the resultant force is happening. Okay, and from that point to the surface, that is LP. Okay, in the left hand side, HC is the depth from the surface to the center of the wall, and HP is the depth from the surface of the fluid to the center of pressure, where the resultant force is happening. Okay, now in order to solve the problem, remember how I told you that if we're looking for the resultant force, it equals to P average times A. Now this A, as I said before, I shown you that it is the area in contact with the fluid, which is width times length. In order to find the area, we need the length. And in order to find the length, we have to use this triangle here. LC, no, actually L and H with this angle here, inclined. So this is L, this is H. We're going to use H to find L, given this angle here. So it'll look something like this. This is L, the inclined length of the wall. This is H, the depth of the wall, of the fluid, sorry, H, which equals to 10 meters. And it's perpendicular. Okay, this triangle is perpendicular. And the angle is 60 degrees. Now, using geometry, sine 60 equals to the opposite over the hypotenuse, which is H over L. Therefore, L equals depth of the fluid over sine 60. Okay? And with that step here, we found the area. We found L, therefore we found the area. Okay? The width is given. I am pretty sure I wrote that. No, I erased it. So width is 20 meters. Okay? Now, the second step after finding the length of the wall is to find the resultant force. So resultant force equals average pressure, which is specific weight of water, times HC. That's average pressure. And the area is length of the wall times the width of the wall. We usually, in the previous example, we used the depth H for L, but since now the wall is inclined, we can no longer use the depth of the fluid for the length of the wall. Since it's inclined, we have to find it. Okay, so the specific weight of gravity is given, HC is known, L we found, and the width is given. So we have our resultant force. Now the second step is to find where is the resultant force happening. So if we take the same triangle, which is L, the inclined wall, H, the depth, and the angle of inclination, which is 60, and it's a right angle triangle. Now, we know that pressure acting on the inclined wall at the surface, the pressure is 0, right? And as we go deeper and deeper into the fluid, the pressure increases. Okay, now, therefore, actually we don't need this triangle here. Just look at the inclined wall, L, and we know that the pressure at the surface of fluid is 0, and as we go down, it increases. Okay. So HP is 1/3 of H from the bottom, and from the top is 2/3 of H. Now from top, okay, now HP equals H, the total H, minus 1/3 from the bottom, or HP, this is in order to get it from the top, to get using the top as a reference point. Top, you'll be fine if you write 1/3 of H from the bottom. You're okay with that, but I usually like to reference it from the top. So if I calculate it from the bottom, I'll say HP equals H minus 1/3 of H in order for it to be on the top, okay? Or it will equal to 2 over 3 of H from top, okay? Now, we also need to find the distance of L from the top of the length of where the center of pressure is happening. So LP equals 1 over 3, same thing, of H from bottom, and it also equals to 2 over 3 of H from top. Okay, that's it for this class. This is a pretty simple example, but when we get into submerged planes, which are irregular shape, something that looks like this, for example, we'll see it in the next class, hopefully. Okay, we can't just say that HP and LP is 1/3 of H from the bottom. Okay, there's an actual equation used to find HP and LP, whereas since this is a simple wall, one is vertical and the other is inclined, we are able to use these laws right here. Okay, that's it for this class. See you in the next one.